Hello advanced algebra students, welcome back to another video lesson. Today on 6-4, how we can look at the graph of standard form, y equals ax squared plus bx plus c, and apply it to problems with projectiles in motion, which uses what's called Newton's formula. Yes, the guy that the apple fell on his head, that Newton. All right, and so really we're looking at this standard form and how does it apply to a graph. But more so, how can we define the height of an object over a certain amount of time? Right. So if you ever played Angry Birds, you slingshotted a bird, and eventually, depending on how fast or how quick you launched it, it had this projectile in motion that would define how far it goes. Or even people on like half pipes and ski jumps, if they go up, they're in motion for a certain while, and then they eventually come back to the ground. And we're going to use formulas that'll help us to slowly identify their distance or their height off the ground over a certain amount of time. Now, in order to do that, we need to know what Newton's formula is. Now, don't write this down quite yet, because this is the general formula for Newton's objects in motion, where G stands for the gravitational kind of pull in a sense, but we use certain things for G depending on how we're measuring our distance, okay? So the two equations that you really want to make sure that you have written down are these two. One of them represents when we're talking about units of measurement in feet, where the other one is in meters. So it'd be a good time to pause the video and write those down. Okay, first one, h of t, right? So this h of t really represents our height function. How high is the object given a certain amount of time? -16, that's for feet. T squared plus v sub 0 t plus h sub 0. We're going to talk about what the h sub 0 and v sub 0 mean in just a moment, because the second equation is exactly the same. All the same pieces except for the front piece, -4.9, which represents the translation to meters. Okay, and so it's still representing the height of an object if we plugged in some value for time. But we got to know what v sub 0 and h sub 0 are. Okay, let me delete that. V sub 0 stands for the initial upward velocity. How fast is something flying upwards, right? What's that velocity that it's going at? Where h sub 0 stands for the initial height. How far is something off the ground before it's being projected into the air? Think of throwing a baseball up into the air or a softball, right? You're not throwing it from ground level if you're certain tall. You're throwing it from wherever you're letting go, so it's already got some momentum off the ground. So that's the initial height. The velocity describes how fast it's going. Make sure you have these formulas down and make sure you know what these particular pieces represent. The t is time. We're going to end up putting different values in there to see how high an object might be after 3 seconds or 2 seconds and things like that. Now, there's two other caveats to what's going on here that we have to make sure we understand. One of them talks about when something is just being dropped, like from a bridge or from a cliff, right? When you're just dropping it. The other one talks about when it starts on the ground, right? Kicking a soccer ball or kicking a football off to start a football game. If something is being dropped, the key word here is dropped, it has 0 for the upward initial velocity. Right? We're not throwing it up into the sky at all. We're just putting our hand out and letting it go. Parachuters falling out of a plane if you're skydiving or something like that. Right? It doesn't have an initial upward velocity, so it's 0. The second one, if we're kicking something from the ground, right? It's starting on the ground. Its initial height, that h sub 0, is going to be 0. Right? Because that's how far it is off the ground. It doesn't have any extra height already added to it. So those are two key pieces that you need to kind of remember when you're working with some of these different problems and equations. So here's an example, just looking at the equations and trying to identify the key features, the key pieces based on what is written. This is from your packet. Fill in the table given the models, okay, given those models. So let's just focus on this first column here. H of t equals -4.9 t squared plus 6.1 t plus 4. Is this meters or is this feet? Hopefully you remember, and I wrote them, they're down below. This is representing something being measured in meters. What's the initial velocity, right? How fast is it being thrown? Well, that's this value v sub 0, which is directly in front of the t. So in this case, 6.1, and we say meters per second, right? Meters per second, typically. That's how fast it's going. And then its initial height, right? How far off the ground is it already? Well, that's the constant out here, h sub 0, so that would be 4. The second one, negative 16t squared plus 15t. Hopefully, you recognize that's feet. What's the initial upward velocity? Again, that's the value in front of t, so 15. In this case, it's not meters, but 15 feet per second. Usually it's per second. Sometimes they might measure it in minutes. Who knows? Then what's the initial height? What's the h sub 0? Notice there isn't an h sub 0 out here, which means it has a 0 feet height off the ground. It's starting on the ground, right? It's actually starting on the ground because there is no value out here on the end. Last one, negative 4.9 t squared plus 11. So they're using negative 4.9. Again, that's meters. So we're looking at how are we measuring something here in meters. The initial velocity, how fast is it going up? Well, notice that's always in front of t. Do we have that middle piece here? Do we have a t value? No. So the initial velocity here is 0 feet per second, which means it is being dropped. It's not even being thrown up, it's just being dropped. What's the initial height? Where is it starting at? 11 meters. So that's how we can interpret the equations in standard form that they give us for projectiles in motion. Let's look at what this probably looks like more so in an example, though, right? So hopefully you've had water balloon fights before, but Jen is throwing a water balloon upward into the air from an initial height of 5 feet. So that's kind of where she's releasing it out of her hand at 5 feet with an initial velocity of 30 feet every second. That's pretty fast, right? It's traveling 30 feet in 1 second. Step number 1, write an equation relating the time in seconds at the height of the ball. So this is going to be h of t, right? The height based upon its time in seconds is going to equal. Now we have to determine, are we talking about meters or feet? In this case, we're talking about feet. So that's the negative 16 t squared plus v sub 0, which is the initial velocity. How fast is it being thrown? So 30, so plus 30t plus the initial height. What's the h0, the initial height? It's starting 5 feet off the ground. So that's our equation. That's what we're truly looking for. That's going to help us graph, and it's going to help us figure out question number 2. Find the height of the ball after 1.5 seconds. Find the height. That means we need to plug 1.5 in for all of these t's and then evaluate. Negative 16 times 1.5 squared plus 30 times 1.5 plus 5. Now you can go to Desmos, you can go to your calculator, you can do whatever you need to punch this in, and you're going to get an answer that the height after 1.5 seconds, if you punch it in correctly, should give you 14 feet. Right? The height of this water balloon after 1.5 seconds, it's already coming back down because it's at 14 feet. What is the maximum height of the water balloon? When does it hit the ground? These are questions that we're going to have to answer by using Desmos, right? The only way to answer the maximum height, which is the vertex, we're figuring out when it comes back to the ground, is by going to Desmos and punching in our equation. So I'm going to go over here to Desmos, and let's type in y equals negative 16x squared plus the initial velocity was 30 feet. The initial height was 5. Now you have to use y and x in Desmos. You can't use the h and t. which is okay. And I'm going to zoom out and I'm going to change my window. Let's do -2 up to, let's just talk about 10. And let's go from -2 on the y-axis all the way up to 50. Let's just see what happens if we use 50. All right, there we go. So the questions asked us, this is the path of the water balloon, right? We're really only looking at quadrant 1. When time was 0, it started at 5 feet off the ground. When the time was 0, that's where she was letting it go. And then it traveled this path. It went all the way up, and then it came all the way back down. Now notice, when I clicked on that intercept, it gave me 0, 5. It also gave me a point down here, 2.2090, and then a point up here. We need to interpret what all of those different points might represent. So this is the vertex, or the maximum height, 0.938, 19.063. We also know that this point over here is 2.029, 0. What does this point represent right down here at the end? Right, what does this line represent? That's when the water balloon reaches back down to the ground, right? Our y-axis represents the height of the water balloon, where the x-axis represents our time. So I'm going to want to make sure that we copy all of that down. I just wrote it over here on a piece of paper. And now we're going to answer the questions. What's the maximum height of the water balloon? Well, that height was up here with that point, which was 0.938, 19.063, or 19.1 feet, roughly, right? The height. How high was it at that time? And we could also answer at what time did that happen by going back to the graph. When, right? What time does the ball hit the ground? So we know it hit the ground over here, but what time was that at? 2.03 seconds. 2.03 seconds. Okay, and again, I'm getting that from this graph. How high was it? That's the y part. When did it hit the ground is the x value. So use Desmos to help you find that information. If you need to make a sketch of it, right, we should know that if this is a 1 and this is a 2, if I'm counting correctly and labeling it, accurately, that it reached its max right here. It hit the ground right here. So we're going something like this, and it's coming back down, and it left at a y-intercept of 5, right? So the y-intercept, the important key points, the y-intercept was 5. The vertex was at the point 0.938, 19.1, and the x-intercept, was at 2.03. That's when it came back to the ground. And so those are the key things that you're looking for from that graph, right? The y-intercept was 5. That's where it left my hand, 5 feet off the ground. It went all the way up here as a water balloon, and at 0.9 seconds, it reached a height of 19.1. Then it slowly started to come back down to the ground and eventually hit the ground at 2.03 seconds. That's how we can use this projectile in motions and Newton's formula. You're going to have some practice problems out of the textbook today, and we're going to practice more on Monday leading up to a test. So take your time. Let me know if you have any questions, and don't hesitate to reach out. Until next time, everyone, stay safe.